Bismillah ar-Rahman ar-Rahim. This is the fifth video on adaptive control. This course is taught at the Faculty of Engineering in Cairo University. We are still talking about the interpretations and properties of the least squares estimation. We have started talking about the statistical properties. We will continue that in this video, and we'll go on and see the geometrical interpretation as well. The basic theorem that gives the properties of the least squares estimate under ideal conditions assumes that we have measurements y, and that measurements is contaminated by noise. This noise under ideal conditions are assumed to be an independent sequence of zero mean and variance sigma squared. So in that case, the least square estimate theta hat is equal to phi transpose phi inverse times phi transpose y, where the matrix phi contains as rows the regressor or the data vector, which is given here the symbol small phi transpose, and the elements of the vector y will contain the measurements of the output at the different instance of times. This is a batch processing procedure that we are going to develop later on to be recursive in order to use it for adaptive control. Anyhow, the basic properties say that under these ideal conditions, the least square estimate that we produce using the least squares would be unbiased, which means that the expected value of the estimated parameter theta is equal to the true value. The covariance of the estimate would be equal to the variance of the noise multiplied by phi transpose phi inverse, and the significance actually of this matrix is that its diagonal elements will be the variances of the different estimates in the vector theta. Of course, as these variances get smaller, that means that we will have more confidence in our estimates. The off-diagonal elements of this matrix will give the relation between the different estimates and each other, and of course in ideal situation the off-diagonal elements have to be zeros. Now if we don't know the variance of the noise, we can have an estimate for that variance, and that is given by the summation of the squares of the residues divided by the number of data points minus the number of parameters, and this is an unbiased estimate of the variance. Now let's see how we can implement the least square estimate formula using a simple example. If we assume that we have an output which is related to previous output and yk minus 1 and yk minus 2, and previous input uk minus 1 and uk minus 2, and we have a table here which is in terms of a batch data, which means that we have for different instance of time k from 0 up to 9, we have the corresponding measurements of the input and the output. Now in order to form the vector y, we will notice here that we will need always two samples delay in order to construct the regressor, which means that if I have y of k, I will need k minus y of k minus 1 and yk minus 2 in order to construct my regressor. That's why when forming the vector y, I start here from the third sample 0.24, because I know that I will need the previous two samples at 1 and 0 in order to construct my regressor, and similarly for u, and this comes from the given equation of the system. So we can see here, if I take y of k as y of 2, then I will need here y of 1 and y of 0, and that's how I build the first vector in the matrix phi transpose. So this is y of 1 and y of 0 stacked here, and then I continue. This is u of 1 and u of 0. So this vector is what I call small phi vector, and so on for the rest of the values. So if we construct the matrix phi and vector y, we can just implement the formula and we get the parameters, the unknown parameters of the system, which are given by these values. Now I can calculate, assuming that I don't know the variance of the noise, so I can calculate the variance of the noise by calculating the residue, which is y minus phi theta hat transpose time y minus phi theta hat transpose. That will give me actually a summation of the elements of this vector y minus phi theta hat, summation of that, the squares of the elements of this vector, and then I divide by, as we mentioned before, number of data points minus number of parameters, and that will give me the estimate of the variance. Consequently, the covariance matrix of the estimates will be phi transpose phi inverse times sigma hat squared. So knowing phi, knowing sigma hat, we can calculate the covariance matrix. And as we mentioned before, the diagonal elements here will give us the variances of the different estimates. So the variance of alpha 1, for example, is 9.7 times 0.0012. If I'd like to calculate the standard deviation, I would take the square root of that value. If I'd like to get the region of say 95% confidence, then I would say that the actual value of alpha 1 would be in the range 1.35 plus or minus 2 times the standard deviation as calculated, and so on for the rest of the values. Now let's talk about the geometrical interpretation. Now the residue is y minus phi theta. I can write this equation in another way. Since we are multiplying the matrix phi by a vector theta, so this multiplication could be a summation of the elements of theta times the corresponding columns in phi. So that means here I have y minus first column of phi times first element in theta, and this would be theta 1, then second column of phi times second element of theta, and so on till we finish all the elements of theta, which I'm assuming to have n parameters. Now in order to give a geometrical interpretation, I'm going to assume that I only have two unknown parameters, a two-dimension vector phi, so in that two-dimension vector theta, so I have only theta 1 and theta 2. In that case, phi 1 and phi 2, the regressors here, would define a certain plane, and phi 1 times theta 1 plus phi 2 times theta 2, that would define a vector y hat in the plane of phi 1 and phi 2. Now the actual vector of measurements y is not necessarily in the same plane, so I'm assuming in general a vector y to represent the collected output measurements in a third dimension as shown here. Now E is equal to phi minus phi 1 theta 1 minus phi 2 theta 2, so that means I have here y, I have minus that vector which is y hat, so the difference y minus this will give us the vector E, which is over here. Now the least square requires that I choose the value of theta 1 and theta 2 so that this difference is minimum. Now we know from solid geometry that this vector is minimum if it is perpendicular uh, to the plane of phi 1 and phi 2, or in other words, the shortest distance between the tip point here of y and the plane would be the perpendicular distance, which is defining E here. If E is perpendicular on the plane which is defined by phi 1 and phi 2, it means that E is perpendicular to every vector in that plane. So I can write that the inner product of phi and E will be equal to 0, because we know that the inner product is nothing but the magnitude of the first vector times magnitude of the second vector times the cosine, the angle between the two vectors. So if that angle is 90, it means that we will have a 0 here. So if I take that for the two vectors phi 1 and phi 2, I will get this equation. Now if I write the two equations for phi 1 and phi 2, I will end up with the matrix phi transpose times the error vector, which is y minus phi theta equal to 0, and this equation will give me again the least square formula as we derived it before. Finally, if we would like to give a different weight for the different errors or different residues, then we can write our cost function as 1/2 E transpose omega E instead of E transpose E as we did in the least squares, and the modification in the resulting formula would be just by adding W here in the formula for theta hat. So it would, the least square estimate in that case would be phi transpose W phi inverse times phi transpose WY. This can be proven the same way that we proved the least square formula.